All right, let's talk about polar coordinates. If you've ever stared at them in a calculus textbook and just saw a bunch of weird formulas to memorize, you are definitely in the right place. Today, we're going to demystify the whole thing and build a real intuitive feel for what these are and why they're so incredibly useful.
Okay, so to get started, we really just need to shift our perspective. We're all super comfortable finding our way around a map using a grid, right? But we're about to explore a totally different way to describe where something is, and in a lot of cases, it's a much more natural way to do it.
And this slide is the perfect way to think about it. Our good old Cartesian system, the x, y points, that's like a city grid. You walk 3 blocks east, 4 blocks north. It's all about horizontal and vertical moves. Polar, on the other hand, is like a radar station. You point in a certain direction, that's your angle theta, and then you say how far to go in that direction, that's your radius, r. It's all about direction and distance from one central point.
So how do we actually connect these two worlds? How do we translate between the city grid and the radar station? Well, we need a toolkit. But these aren't just random formulas, I promise. They are the logical bridge that lets us move back and forth between these two ways of thinking.
So let's start with what we already know. Here's a point, x, y, on a normal graph. We've got our horizontal distance x, our vertical distance y. Super simple. We've seen this a million times. But now watch this. As soon as we draw the line straight from the origin out to that point, boom, a right triangle just appears, like it was hiding there the whole time. And look, the sides are our x and y, the hypotenuse is our polar distance r, and that angle down at the origin, that's our polar direction, theta.
And since it's just a right triangle, we can use basic high school trig, SOHCAHTOA, to get all the conversions. The adjacent side, x, is just r times the cosine of theta. The opposite side, y, is r times the sine of theta. The Pythagorean theorem gives us r squared equals x squared plus y squared. And finally, tangent of theta is opposite over adjacent, which is y over x. Seriously, that's it. Those 4 formulas are the entire toolkit.
Okay, so the theory seems pretty straightforward, right? But there are a couple of classic traps that trip a lot of people up when they're starting out. So let's just tackle them head on right now so you can sidestep them completely.
Let me ask you a quick question. If I tell you that the tangent of an angle is 1, what's the angle? Your first instinct is probably to grab a calculator, punch it in, and get an answer. But is that the only answer?
And here's where the trap is. Your calculator is going to spit out 45 degrees, which is totally correct for the point 1, 1. But look down in the third quadrant at the point -1, -1. What's the tangent there? It's -1 divided by -1, which is also +1. So the angle could just as easily be 225 degrees. If you only trust your calculator, you could end up in the completely wrong place.
So what's the secret? How do you avoid this? It is the single most important piece of advice for this topic. Always, always draw a quick sketch. Just plot your x, y point and see what quadrant it's in. That simple visual check will save you so much trouble.
Okay, the other concept that can feel a little weird at first is a negative radius. I mean, what does that even mean? Think of it like this. You aim in the direction of the angle, but instead of walking forward, you walk backwards that distance. So pointing yourself at 30 degrees, but then walking backward 2 units, puts you in the exact same spot as pointing at 210 degrees and walking forward 2 units. It's just 2 different addresses for the exact same location.
All right, converting single points from one system to another is cool and all, but the real magic of polar coordinates happens when we start converting entire equations. This is where really complicated-looking shapes can suddenly become super simple and vice versa. Okay, get this. The equation is r equals 2 sine theta. Looks pretty weird, right? But watch this little trick. Let's multiply the whole thing by r. Now we have r squared on the left and 2r sine theta on the right. Why on earth would we do that? Because now we have pieces we recognize. R squared is just x squared plus y squared, and r sine theta, that's just y. After a little bit of algebra, we find out this weird polar equation is just a simple circle centered at 0, 1. How cool is that?
Now let's try going the other way. What does a shape we know really well, like a simple parabola, y equals x squared, look like in polar form? Well, we just substitute our formulas. Y becomes r sine theta, and x becomes r cosine theta. We do a little bit of simplifying, and we end up with r equals tangent theta secant theta. Yeah, not nearly as nice and clean as y equals x squared. It just goes to show you that some things are easier in one system and some are easier in the other.
Let's do one more, just to really lock this in.
Let's convert r equals -4 cosine theta. We're going to use our little trick again and multiply by r. That gives us r squared on one side and -4r cosine theta on the other. We know what those are. We substitute them in, complete the square, and look at that. It's another circle, this time with a radius of 2, centered at -2, 0.
So we've been doing a lot of math here, converting points and equations, but you're probably asking yourself, so what? Why does any of this actually matter outside of my calculus class? And that's a fantastic question. The reason it matters is that a ton of stuff in the real world is built around a central point, all about direction and distance.
And a perfect example of this is in the world of audio, with something called a microphone's polar pattern. And that's not a metaphor. It is literally a polar graph that shows you how sensitive a microphone is to sounds coming from different directions. Take this one, the cardioid microphone. It's super common. Its pattern looks like a heart. That's what cardioid means. And if you look at the graph, you can see it picks up sound really well from the front at 0 degrees. But it basically ignores anything coming from the back at 180 degrees. This is exactly why a singer on stage sounds so clear, while the roar of the crowd behind them gets canceled out. It's all described perfectly by polar coordinates. So, what's the big takeaway here? Polar coordinates aren't just some abstract math topic. They are a genuinely powerful new lens to see the world through. Now that you can think in terms of direction and distance, what else starts to make more sense? Think about the spiral of a nautilus shell, the spray of water from a sprinkler, or the orbits of planets around the sun. How could this new point of view describe them more elegantly?